My name is Paul Nation. I'm a research staff member at our TJ Watson lab for IBM. This is where all of our quantum team lives and plays. Okay, and I'll just give you a brief overview of basically what we do as a whole at IBM. Okay, so one thing that hasn't been touched on yet is, of course, why we are here. And I'm pretty sure that everyone in this room has seen some kind of news article about quantum computing that says quantum computing will do, maybe do, possibly can do one of these things, right? Portfolio management, quantum chemistry, etc. Okay? And there's lots of coulds, woulds, and maybes, okay, because that's really the most we can say at this time. Okay? The best we can say is what can we do today? Okay? And so currently what we can do is just basic representations of those things I just showed you. And this is because, as we've heard before, near-term devices, and by near-term I mean today, tomorrow, 5 years from now, maybe even 10 years from now, our devices are noisy. Okay? These go by the name of NIST devices, noisy intermediate scale quantum devices. Okay? Our devices are not error corrected. That is very, very hard to do, but we can do basic like noise mitigation, right? So you can clean up your data somewhat, right? Our devices have limited effective computational power. I'll talk about that in just a sec. You can't actually do too much with them, to be honest, okay? What we can do is we can come up with novel algorithms focused on using what we call short width and depth circuits. So width here means the number of qubits. Depth, if you don't know what depth means, you can just think about that as the amount of time it takes to run your computation. So small numbers of qubits, short amount of time, okay? And we have to do that because we have to play within this time scale set by our noise, okay? And of course, here are some examples of this that was worked on at IBM for things like quantum chemistry and machine learning on actual quantum processors, okay? All these kind of algorithms are heuristic algorithms, typically hybrid algorithms. We've heard that mentioned a couple times today, okay, where it is possible to have a quantum speedup, but it's not proven. Okay, so we can't actually prove this. And it turns out that if you actually want to prove a quantum computer can do something faster than a classic one, it wasn't until this paper here at the end of last year that it was actually proven by work at IBM on really short depth circuits. Okay, so this may seem kind of disappointing, okay, but it turns out that this is actually really cool, and if you put it in context of the journey that was required to get here, it's even more impressive, okay? So this journey started about 85 years ago, depending on how you want to start counting. I'll start counting with the EPR paradox and the idea of entanglement, and you can go from there. In '81, this is the conference that Feynman was at, where everyone steals his quotes from. You can go down, we've heard of things like quantum cryptography, etc., and you can come all the way down to the present day. Okay? A couple of these guys are highlighted in yellow or orange, depending on your definition of color. Okay, and these are all just points in this timeline where IBM played a role. Okay? Actually, most of the work done in the lab I showed you on my title slide. Okay? But to put things in context, here in 2007 was the introduction of the superconducting transmon qubit. This is the qubit that we and other teams that work on superconducting devices use as the basic building block of their device, and that was mathematically formulated in 2007. So just 10 years on, we now have quantum devices from this. Okay, this timeline can kind of be broken up into 3 different pieces. We've only reached 2 of them at this stage. The first one is the regime that we call the quantum science regime, and this is basically you have to come up with the fundamental theoretical and experimental building blocks upon which you make a quantum computer. And that started in earnest in the 1960s, again, depending on who you ask. Okay, and of course that will continue on forever. All right, we're always learning. All right, but we have now entered another regime, which we call the quantum ready regime, where we've reached a point where we have devices that can do interesting things. And so we have to start to prepare people for how to use these devices. What limitations do they have? What tools and tricks do you need to know to take advantage of them? And of course, at some point, we have to demonstrate that a quantum computer can actually do some task of importance better than a classical computer. Okay? We have to demonstrate that at some point. And of course, the regime that we haven't reached yet is the regime that we call quantum advantage, where you will actually get a benefit from running on a quantum computer. And by advantage, that could be speed, it could be cost analysis, there's various benchmarks, but there will be tasks that a quantum computer is better than a classical. Okay? And then you can see that these things, there's 2020s here, there's 2050s, there's squiggly lines, all right? That's a very big squiggly line, okay? But there's only one date on here that does not have a squiggly line, that's 2016, okay? Because if you want to have people take advantage of quantum computers, you have to actually put it in their hands, okay? And IBM did this in 2016, which is why that's a firm date, okay? This is when we unleashed the IBM Quantum Experience, which was the first online, publicly available cloud service where anyone in the world can start running on actual quantum hardware. Here's a picture of the early interface of this. It was a 5-qubit device. You can kind of see this little bow tie shape here. Okay? And at the time this was released, I was actually at a different company. Okay? And at a different company, people laughed at this because they said it's 5 qubits. That's a 32 by 32 matrix. A computer can crunch that. Okay? But what's unsaid is not just that it's 5 qubits, but those 5 qubits are stable. Okay? They are online 24 hours a day, 7 days a week. Okay? Some of our devices have been online for 2 to 3 years. Okay? And they just continuously work. You also have to have the entire infrastructure to support this, where people can actually talk to a device, get data back, etc. Okay? So to this date, okay, IBM is still the only company here that actually has a publicly available quantum cloud service where you can talk to a real quantum device. Okay? So that shows you how difficult it is. All right? And so you can also ask, is this successful? Okay, and of course, when you first do this, you're not quite sure. All right, but let me play a little movie. Okay, these are the users as a function of time. The red down here is simulator runs, and the blue is actual hardware. Right? And so while this runs, you can see where the users are coming from. Okay. Right. At the bottom, I just point out that as of to date, there's about 190 academic articles written about or written because of results on the quantum experience. These are not IBM articles, these are other people. 5 million real experiments, and by real I mean on actual quantum devices, not the simulator, okay? Each experiment includes running circuits multiple times. If you aggregate all those, then you're up to 5 billion plus quantum circuits run. Okay? So that's a lot of quantum circuits. Right. Another interesting thing to note, this goes out to about March of this year. You can see that as a function of time, the usage of the quantum chips has basically become equal to the usage of the simulators. If I was able to show you the data that is beyond March of this year, you would see that we have reached a crossover point. Okay? People run more now on the quantum chips than they do on the simulators. All right? And so that's actually an amazing thing. Right? There is more value in running on a quantum device at this point in time than there is to actually simulate. So the question is, why is that? And the basic answer is our devices get better over time. Right? So here are the basic device characteristics for a couple devices, the ones that are actually online. Okay? And these are organized by time. So here are the dates, and these are the dates the devices first came online. Okay? As a public user, you don't have access to all these devices, but these are the ones in principle you could have access to. So here in the blue is the controlled not error rate, the average error rate for a given device. Again, this orange here is the readout error of our devices. And these green guys here, the squares are the T1 times, and the stars are the T2 times of our devices, right? These are the coherence times. Right? And then this axis over here measures those times. And you can see as a function of time, these devices are ordered by time as well. This was the first device, the second device, third, fourth, fifth, and sixth. You can see that as you go over, there's a trend in the data. And the trend is that as a function of time, the coherence time is going up, and your gate errors are going down, right? So with longer coherence time, you can do more gates, and those gates that we do are higher quality gates. right? So we're winning on both fronts, okay? If that was not enough, this is all being done at the same time as our devices are getting larger, okay? And if you know anything about device physics, you know that as your devices get larger and they have more connections, things become more noisy, all right? So this is actually pretty incredible. Right? And there's a reason for this, okay? And the main reason that we're able to do this is because we take a different strategy than with the other superconducting circuit companies out there. All right? We use what's called a fixed frequency transmon qubit, whereas other people use a tunable frequency qubit. Right? And there's advantages and disadvantages to both, but the idea is that if you have a flux tunable transmon qubit, you can control the frequency of your qubit. Right? By applying a magnetic field, I can tune it to almost anything I want to within reason. We do not have that ability. Okay? But on the plus side is that, again, if you have something that can control a qubit, that also introduces noise. Okay? So if you have a flux tunable qubit, you have flux tunable noise, or sorry, flux noise. Right? We do not have that. And so because we don't have flux noise, we have very good stability and high coherence. Another thing that's talked about less is that in our devices, we can do all microwave control for single and 2 qubit gates. Okay, we don't have to have separate control electronics. So we can optimize a single set of control electronics. On the downside, we have things that are called frequency collisions, which basically means if your qubits are too close in frequency, you have problems. Okay, and this means you have to be very good at junction fabrication. Okay? So we decided that no flux is the way to go, and the cons, of course, you don't live with, you try to engineer away. Okay? Now, everything I showed you are numbers like T1, T2, C0 errors. These are just small numbers, and you can ask yourself, well, do these numbers mean anything if I'm trying to run an actual algorithm? At the end of the last talk we heard, we would like a full system benchmark of what a quantum computer could do. Okay? And at IBM, we put our heads together and we came up with this idea of the quantum volume. Okay? The quantum volume is a full system benchmark. Okay? It is platform agnostic, right? Trapped ion people can run it the same as we can. Okay? It uses random circuits to try to encapsulate everything you want to know about a quantum computer and analyze it and return just a single number. So here is essentially a marketing plot for quantum volume. Here on one axis is the number of qubits. On the other axis here it says error rate. And error rate here is loosely defined because essentially we're grouping all the possible error rates that a quantum computer could have into a single axis. But the basic idea behind quantum volume is if you just have a large number of qubits, it does you no good computation, right? If you have just a few qubits, but you have very, very good error rates, that still doesn't do you very good because you're limited to the number of qubits. In order to have a quantum device that you can say has X amount of computational power, you have to have a reasonable number of qubits with a reasonable number of, a reasonable error rate. And if you want to do better, you have to increase the qubits at the same time reducing your error rates. Okay, and that's what's kind of pictorially represented here by these enlarging cubes. Okay. And again, this is a full stack benchmark, so it's your hardware, your error rates, the stability of your control electronics, and something that is talked about a bit less is the classical software you use to optimize your circuits. Okay, that actually turns out to be equally important as things like your control block error rate. Right? And here's some results for our devices. So here is the quantum volume for the 4, 8, and 16 for these devices. The devices are, these are the names we give them. These are named after research labs. Tenerife is a 5-qubit device that was released in 2017. It is still online. Tokyo is a more complicated 20-qubit device at 18. PeQC was also 18. And then IBM System 1, which I'll show you at the very last slide, is this shiny looking thing that was released earlier this year. Okay? And so you can see that for quantum volume 4, okay, you can see that all the devices are above this 2/3 line, The 2/3 line we heard a bit about. It's just a way of saying success in a random unitary type algorithm. So you can see that all the devices are able to do a quantum volume of 4, okay, including the device in 2017. A quantum volume of 8, the old device couldn't make it, but the newer ones could. And finally, a quantum volume of 16, only our newest device in 2019 could actually achieve a quantum volume of 16. Okay? But what we can say is that as those devices get better, and they get better every year, the quantum volume that our devices are able to achieve doubles every year. Right? So we have exponential scaling of this quantum volume. Now, this last guy over here, this system 1, quantum volume 16, it turns out that the success of this depends highly on how you optimize your circuits. Okay? If you just send your circuits in without any optimization, you do not actually achieve the success rate. Okay? You actually have to be very good at optimizing your circuits, right? And that requires classical software. So of course we have classical software. This is what we call QISKit. Okay? And QISKit is broken up into elements. These are all named after Greek elements. All right. And there's basically 4 of them. Terra, the ground floor of our software stack, is where you create your circuits. You can also do pulse control, which I won't talk about very much here. And you optimize your circuits or pulses for running on your quantum devices, and this is where you actually send them to your hardware as well. Okay. There's other things. There's air. These are classical simulators, debuggers, and emulators. Ignis is a more specialized error characterization mitigation thing. And then on top of all this is another element called Aqua, which is our algorithms and applications. Okay. So the main one is Terra. This is open source software in Python. Here's a little Jupyter notebook that I'm just creating a 5-qubit GHZ state on. Right. Again, you can send this to your hardware here. I've run this on a 20-qubit device. You can see that it's working pretty good. Unlike a simulator, you see that I get some noise, and if you want to say, hey, what's the noise characteristics of my devices? You can actually see those. We tell you everything you want to know about a device. Okay, we're not hiding anything from you. And again, for things like quantum volume, circuit rewriting tool chains, optimization things, this is very important. And this is actually one of the highlights of our software. Here on the last panel here is a diagram of a circuit rewriting tool chain, which we call transpilation. Okay, and how you go through this graph structure and which pieces you pull in and out can actually make a very big difference on what your circuit is when it runs on the hardware. Okay? Whether it be swap gates, single qubit gates, whatever. Okay. The other elements I don't have too much time to go into. You can go to qiskit.org. Again, air, high performance, scalable quantum simulators, state vector simulators, chasm simulators, Clifford simulators if you really want to do large numbers of qubits, decision tree things, GPU-based things are coming out soon. Very easy to do noise modeling. You could actually query a device and say, what's your noise properties? Give it to air and we'll make a noise model for you. You don't have to think of how to make a noise model. Right? We also have cloud-based simulators that do 32 qubits and beyond. Okay? And all this stuff is always free. There's companies out there that have quantum simulators and they charge money for it. If you're paying money for it, you're a sap. Okay? These are always for free. We're interested in hardware. Right? Ignis is things like actually characterizing T1, T2, do randomized benchmarking. If you don't believe our results for quantum volume, right, you can actually run it yourself. Right? Also things like noise mitigation. And then Aqua, there's too much to go into Aqua, but if you want to do variational quantum eigensolving but don't want to write your own, you can. We heard QAOA, quantum phase estimation, etc. There's a lot of stuff there. Okay. So we have a lot of stuff, but how do you know if the community actually likes it? Right? You don't want to be building a lot of stuff and no one uses it. So here's a couple benchmarks. So here is the number of GitHub forks, so just people who make copies of your repository as a function of time. For our IBM Qiskit, Microsoft is not a fair thing because it's just their sample code, so it's not fair to do. Rigetti's stuff, Cirq and OpenFermion, and also Project Q is on here as well. You can see that as a function of time, QISKit has been growing quite well, where there's a roughly linear slope to everything. If that's not a reasonable benchmark, GitHub also released earlier this year this used by tag, which says how many repositories use your stuff, right? And so these are the numbers down here as of May 30th of this year. You can see that QISKit is at 122. My old hobby, Q-tip, is there at 59, and you can see that other people are down there as well. The reason that this data is a month old is that some of the people here have turned this off. Okay, so I can't get new data for you. So by the benchmarks we have, we think that we are quite successful. But there's also another part of this, okay, and it ties into the last slide, is we want to have people using our stuff, okay, and we actually want to have a community, that we can do research with and that we can help out and we can learn from, okay? And this goes by the name of the IBM Q network. There's basically 4 parts of this. We have industry clients, and so these are people who work with us to develop algorithms in their particular discipline, looking at use cases, etc. We have hubs. Hubs are regional centers, they're usually universities, sometimes national labs, where they do education, research, support, and actually have industry members as well. Ecosystem partners is just a fancy way of saying that some people just want access and don't want to hear from us. And that's what that means. And then, of course, academic partners, we love engaging with academic research centers. We currently do quite a bit. All right. So here is the IBM Q network, and of course, after I made this slide, it changed. But you can see that at the moment I made this, there's 64 members. You can break this down however you want, but you can see that there's a large number of corporations, universities, and startups who have chosen to work with us on various different levels. So we're quite excited about this. Okay. So the last thing I want to talk about is that we have the network, we have the public stuff, we have the IBM Quantum Experience, the soft Python software. It's all kind of disjoint, or at least it was up until this year. Okay? And so what we decided to do is that this is not a scalable thing, okay, but it all needs to be integrated. So earlier this year, we introduced what we call the Quantum Experience, but I like to call it the Integrated Quantum Experience, or the IQX. And this is essentially cloud services and software that take full advantage of our quantum hardware. And here's a picture of someone actually using it, making nothing, it seems. All right, so here's a little screenshot of this. So it is a website that you go to, right? You log in, and you have access to essentially everything you need to do quantum computation, right? So you can, all your experiments, all your account stuff is in the same spot. Everything is stored on the IBM Q servers, so you can pick up where you left off. Everything is synced together. It has a direct connection to IBM Q hardware. So if you're doing some iterative algorithm, you don't want to wait for a network API, this is the place to build, right? And also, if you were one of these clients that I just mentioned, like a hub where you have lots of members, maybe lots of students, this can all be integrated, and the management of teams and everything is built in. So you can see things like, for example, here I have access to my devices, some circuits that are running, etc. It also has things that the old Quantum Experience had. We have a graphical way of defining circuits. What's improved is that we actually simulate these behind the scenes when you build it. So as I built again this 5GHZ state, it's automatically computing the probabilities, right? So everything is running in real time. If I change this, those things get updated in real time. Let's say you don't know what a 5-qubit GHZ state is. We have documentation where you can find out. All the documentation is integrated right there. You can find out how to get us on Slack, Stack Exchange. If you have questions, it's all built in. But the thing I like the best is we have built-in Jupyter notebooks. We have a built-in Jupyter server, right? So you can actually do your notebooks right in this user interface. All of our QISKit software is already installed. We already know who you are, so all your account information is preloaded, right? So everything is just ready to go. So here I am, I'm making a Bernstein-von-Zerani oracle that we heard a bit about earlier, right? So again, all of my notebooks I can access from a single spot. You can access all of our tutorial notebooks from the exact same spot. And again, all of our notebooks are running on our servers. Everything is saved automatically, right? And there, again, there's no overhead from doing network connections. So it's actually pretty fast. All right. So we're very excited about this. It's being rolled out continuously over the course of this year, and you'll see lots of other stuff that's really cool. All right. So if anything I told you about sounds interesting, I encourage you to go to quantumcomputing.ibm.com. This is where this quantum experience lives. Okay? And if you do so, by the time the next speaker comes up, you will be actually accessing real quantum devices. All right? So thank you very much.